Welcome to This Explainer. You know, when we think about the absolute limit, the ceiling of artificial intelligence, we usually picture silicon shortages, right? Or maybe we think about the limits of processing power. But what if the real bottleneck isn't the microchip at all? What if the ultimate hard limit on AI is actually the very electricity that powers it? Think about it. When you open up an AI chatbot on your phone or your laptop, the whole experience feels entirely digital. It's this weightless, sleek interface with a little blinking cursor. You type a prompt, and instantly, words or images just appear out of nowhere. But that weightless digital experience is rapidly crashing into a very heavy, very physical reality. Because right behind your screen is a world of high-voltage substations humming in the rain, heavy industrial equipment, and regional power grids being pushed to their absolute limits.
Part 1. The physical cloud.
Far from being some fluffy, invisible cloud floating above us, AI actually lives inside massive industrial facilities known as data centers. And these definitely aren't your average office buildings. They are packed floor to ceiling with high-performance servers, completely tethered together by miles and miles of networking cable. They require dedicated electrical substations and massive transformers just to handle the incoming voltage. And because all that computing generates an intense, incredible amount of heat, they need industrial-scale cooling and full-blown water treatment plants. Tech giants like Microsoft and Google are right now re-engineering every single physical aspect of these facilities for the AI era. We're talking about everything from the specific concrete mixtures they use in the walls, all the way down to advanced liquid cooling running directly through the server racks. Part 2, the electricity surge. So all of this intense physical infrastructure is driving a historic and frankly unprecedented surge in national power demand. The data is just staggering. Back in 2014, all US data centers combined used about 58 terawatt hours of electricity. By 2023, that number had completely tripled to 176 terawatt hours, which is roughly 4.4% of total US electricity consumption. But that climb, it is just getting started. The Department of Energy projects that by 2028, total US data center demand could reach up to a maximum estimate of 580 terawatt hours. AI workloads are creating these concentrated, massive electrical loads that our traditional grids were simply never built to handle. To put that 2028 projection into perspective, if that maximum estimate actually hits, data centers could end up consuming up to 12% of the entire nation's power. Just imagine that for a second. Over 1/10 of the US electrical grid dedicated solely to keeping the cloud running. Part 3, heat, water, and grids. Now, when you push this much electricity through processors, you create astronomical amounts of heat. The industry actually tracks this using a metric called PUE, which stands for Power Usage Effectiveness. It's a ratio. A perfect PUE of 1.0 means every single watt of energy goes directly to the computers doing the math. Any number above 1.0 represents overhead, basically the power needed just to keep those processors from melting down, like running fans and chillers. Currently, Google operates at a highly efficient fleet average of 1.09, and Microsoft sits at an average of 1.17. But managing that overhead, keeping those numbers as close to 1.0 as possible, traditionally requires evaporating massive amounts of water. To combat that intense water usage, these companies are developing some pretty extreme solutions. Microsoft, for example, is running a pilot for a newer closed-loop cooling design. So instead of evaporating water, this system actually circulates liquid coolant directly to the hot chips in a completely sealed loop. The savings here are wild. This design alone can avoid the need for an astounding 125 million liters of water annually, and that is just at a single facility. But here's the catch. Even if you somehow perfectly solve the cooling issue, you hit another wall. The primary issue today isn't just generating enough power, it's the physical act of moving it. Local electrical grids are struggling hard to keep up with the breakneck speed of AI expansion. Getting a new facility plugged into the grid requires siting and permitting for new high-voltage transmission lines, which is a regulatory struggle that can literally take years. The traditional grids simply cannot move fast enough to meet these large, super-concentrated power loads. Part 4, the nuclear solution. To completely bypass those traditional grid delays, tech companies are deciding to go straight to the source for long-term energy. A really prime example of this is the Crane Clean Energy Center at the former 3 Mile Island site. Now, this site actually has 2 distinct units. Unit 1 permanently ceased power operations back in 2019 purely for economic reasons. In a truly historic move, Microsoft signed a 20-year power purchase agreement to buy the power generated by restarting this specific reactor. Let's be absolutely clear on the details here. Constellation will independently own and operate the plant, and this project is entirely strictly separate from Unit 2, which is the permanently closed site of the 1979 accident. If regulatory approval is granted and the restoration actually goes forward, the sheer scale of this project is monumental. The goal is to inject 835 megawatts of clean, carbon-free capacity back into the regional PJM power grid by 2027. It really goes to show just how far tech companies are willing to go right now to secure reliable, 24/7 clean energy that is specifically dedicated to their operations. Part 5. The efficiency race. Of course, this massive infrastructure build-out has very real, immediate environmental consequences. In 2025, Microsoft actually reported a 25% rise in their total emissions, and that was largely driven by the massive construction of these new data centers. What's really telling is the spike in their Scope 2 emissions, which represents the actual electricity the company purchases. That specific metric has surged from nearly 2% to 13% of their total footprint. The intense energy appetite of AI is visibly, tangibly altering the carbon footprint of some of the world's largest corporations.
To try and counter these rising emissions, the industry finds itself in a desperate race for efficiency. On the current hardware front, there's some good news. Google reports their compute performance per unit of energy is now 3 times higher than it was just 5 years ago. Looking to the future, experts suggest that combining highly optimized AI models with next-generation hardware and software could actually reduce the energy used for a single task by a staggering 8 to 20 times. And they really have to make the tech more efficient because the physical grids simply cannot sustain unbounded, infinite growth.
Ultimately, we are rapidly entering an era of energy-aware computing. Data centers are no longer just these passive, quiet buildings holding our photos and emails. They are highly integrated, highly demanding physical components of our global energy system. AI is not a weightless concept living up in the ether. Behind every complex model you use is a massive physical system of processors, industrial cooling equipment, electrical transformers, long-haul transmission lines, and increasingly massive, long-term dedicated energy projects. We are reaching a point where the digital and the physical are profoundly, permanently intertwined. As we keep pushing the boundaries of what these algorithms can actually do, we are simultaneously testing the absolute ultimate limits of our physical infrastructure. The central question is no longer just who will build the smartest AI, but who will actually find the power to turn it on. The race for artificial intelligence is becoming a race for electricity.